What happens when you build an engine so powerful that NASCAR bans it before it ever turns a wheel in competition? Ford did exactly that in 1964. And the story behind their 427 Camaro engine is one of the most jaw-dropping tales of mechanical genius, corporate warfare, and underground racing legend that American motorsports has ever produced. We're talking about an engine that was so advanced, so brutally capable, that the people running the sport had to change the rules just to keep it off the track. And here's the thing, that ban might have been the single best thing that ever happened to it. This is legacy motoring, and I spend way too much time thinking about forbidding engines and the underground scenes they inspired. If you're someone who geeks out over the golden age of American muscle, the raw engineering battles between Ford, Chrysler, and GM, and the stories that never make it into the mainstream history books, make sure to hit the subscribe button and give this video a thumbs up if this helps you out. Now, to really understand why this story matters, we need to set the scene. Picture this. It's February 1964. NASCAR executives are sitting in a boardroom in Dearborn, Michigan, and the mood is brutal. They're still reeling from what happened at Daytona. Chrysler's new 426 Hemi had just walked into NASCAR and absolutely destroyed everything Ford put on the track. Richard Petty lapped the field. Plymouth took the top 3 finishing positions. Ford's best effort finished a distant 4th, nearly 4 miles behind the leaders. 4 miles in a race. The Blue Oval's entire racing program was in crisis, and something had to be done. Fast. Here's what most people don't realize about that moment. NASCAR in 1964 wasn't just a sport, it was a marketing battlefield. Manufacturers poured millions into their racing programs because of one simple truth: win on Sunday, sell on Monday. Ford had been spending enormous resources developing their 427 FE engine into a competitive weapon. They'd picked up wins, sure, but Chrysler had been quietly working on something that changed everything. The 426 Hemi featured hemispherical combustion chambers, hence the name, that allowed for massive valves and near-perfect flame propagation across the cylinder. The design actually traced back to aircraft engines from World War II, and Chrysler had spent years perfecting it for racing. The result at Daytona was devastating. Ford's 427s could match the Hemi on raw displacement, but they couldn't touch it in high RPM breathing. The Hemi just kept pulling, where Ford's engines ran out of breath. Look, when you lose that badly on the biggest stage in American motorsports, you don't tweak around the edges. You burn it down and start over. And that's exactly the mindset Ford's engineers brought into the room. The response came from an unlikely corner. A small team of engineers, led by a brilliant and quietly intense man named Al Jonick, had been experimenting with overhead cam designs for a completely separate project, a lightweight sports car engine that never went anywhere. But when the Hemi crisis hit, someone in that group asked the question that changed everything. What if we put overhead cams on the 427? Now here's the thing about overhead cam engines in 1964. They were everywhere in Europe. Ferrari used them, Jaguar used them. They were standard architecture for any manufacturer serious about high RPM performance. But in American V8 engines, that was practically heresy. Detroit had built its identity on the pushrod engine. Single cam in the block, lifters riding on the lobes, pushrods connecting to rocker arms opening valves. Simple, reliable, cheap to manufacture. It worked. But think of it like operating a piano key through a chain of levers. Every link in that chain adds flex, weight, and mechanical lag, especially at high RPM. Overhead cams eliminate all of that. You put the camshaft directly above the valves. Cam lobe contacts the follower opens the valve. Direct, immediate, clean. Ford's engineers understood immediately that this design could rev higher and breathe better than any pushrod engine Detroit had ever produced. The question wasn't whether it would work. The question was whether they could build a running prototype fast enough to matter. They had less than 90 days. What followed was one of the most intense engineering sprints in American automotive history. The team started with the existing 427 FE block because they had no time to design a new one from scratch. But everything from the deck surface upward was completely revolutionary. They engineered a massive timing chain system, actually a series of chains, running from the crankshaft all the way up to overhead camshafts sitting atop each cylinder head. The chain alone stretched over 6 feet. Each cylinder head contained a single camshaft operating 8 valves to precision finger followers. The valve train geometry was close to perfect. Minimal side loading, minimal friction, capable of holding stability at 7,000 RPM in conditions that would have bent push rods and floated valves in any conventional engine. The numbers were staggering for 1964. 427 cubic inches, 4.23-inch bore, 3.78-inch stroke, compression ratio of 12.5 to 1 on racing pistons. The overhead heads flowed 15% more air than Ford's best pushrod units. And here's a stat that made everyone in that room go quiet. With a single 4-barrel carburetor, the Camaro produced 616 horsepower at 7,000 RPM. The street-tuned version, detuned for pump gas with dual quads, still made 657 horsepower. Now, let me put that in perspective for you. A 1964 Corvette with fuel injection made 375 horsepower. The mighty 426 Hemi that had embarrassed Ford at Daytona made 425 horsepower in full race trim. The Camaro was producing 200 horsepower more than the engine everyone considered unbeatable. This wasn't an evolution. This was a complete and total revolution hiding inside a familiar-looking engine bay. The first prototype fired up on April 1, 1964, and the engineers standing in that room couldn't believe what they were hearing. The sound was unlike anything that had ever come out of an American V8. Not the burbling, lopey idle of a big block Chevy, not the deep, authoritative rumble of a Chrysler Hemi. This was a shrieking, mechanical wail that climbed toward redline like a Ferrari or a Jaguar E-Type. Where conventional pushrod engines hit a wall around 6,000 RPM, started gasping, started losing composure in the valve train, the Camaro just kept pulling. 7,000 RPM, and the engine was still accelerating through its power band with total stability. The valve springs held, the chains held, the geometry held. Everything Ford's engineers had theorized on paper was playing out in real time on a dyno in Dearborn, Michigan. Now, you might be thinking, okay, great engine. Why didn't they just race it? Here's where the story gets complicated. Ford rushed the engine to NASCAR officials for approval. They had followed the rules, at least as they understood them. The engine was based on a proven production block. Ford committed to building the required 500 units for homologation. It met the displacement limits. On paper, there was no reason to reject it. But NASCAR officials took one look at those chain-driven overhead camshafts and did something that would define the entire arc of this story. They panicked. Here's what most people don't realize about that moment. This wasn't just a technical objection. This was an existential one. If Ford showed up at Daytona with an engine making 616 horsepower when everyone else was running 400, the entire competitive structure of NASCAR collapses overnight. Chrysler's Hemi, the engine that had just won everything, would be instantly obsolete. Every other manufacturer would be forced into a catastrophically expensive overhead cam development program just to stay relevant. Bill France and the people running NASCAR understood something clearly. The Camaro wasn't just better. It was so much better that it threatened the sport's survival as a competition. On October 19, 1964, NASCAR made their decision official. The 427 single overhead cam engine was banned from competition, deemed, and this is the actual language they used, not suitable for passenger car production. They rewrote the rulebook to specifically prohibit overhead cam engines, a restriction that, in various forms, exists in NASCAR's regulations to this day. Bill France himself reportedly told Ford executives that the Camaro was, quote, too much for the good of racing. Ford was furious, and I mean genuinely institutionally furious. They had spent the equivalent of roughly $10 million in today's money developing this engine in 90 days. They had already completed 50 running engines. They had parts staged and ready to build hundreds more. Henry Ford II personally got on the phone with Bill France to protest the decision. By multiple accounts, that conversation got extremely heated. Ford threatened to pull out of NASCAR entirely, to take their factory support, their money, their cars, and their drivers and walk away. France didn't blink. The ban stood. And this is where the story takes a turn that nobody expected. With NASCAR's door slammed shut, Ford found themselves holding dozens of the most powerful naturally aspirated V8s ever built in America, and absolutely nowhere sanctioned to race them. So they looked at the one major motorsport where nobody was going to tell them what they could and couldn't bolt under the hood: drag racing. The NHRA had no such restriction on overhead cams. If you could build it and it fit within the displacement limits, you could run it. Ford loaded up the cameras and pointed them toward the quarter-mile. And what happened next rewrote the record books. The first camera-powered drag car started appearing in late 1964, and the reaction from drivers who climbed behind the wheel was almost universally the same: disbelief. Guys who had been racing big block Chevys and Mopars, who thought they understood what a fast car felt like, weren't prepared for what the Camaro delivered. It wasn't just a peak horsepower number, as staggering as that was. It was the power curve. The overhead cams allowed for cam profiles that would have destroyed a conventional pushrod valve train, lift numbers and duration figures that kept the intake valves open longer, cramming more air and fuel into those cylinders across a broader RPM range. The engine didn't just hit hard at the top end, it pulled everywhere. Gas Ronda and Les Ricci were among the first to run camera-powered Mustangs in organized competition. At the 1965 NHRA Winter Nationals, Ronda's Camaro Mustang turned in an elapsed time of 10.98 seconds at 127 miles per hour. Now look, those numbers might not stop you in your tracks today, in an era where top-field dragsters run in the 3-second range. But in 1965, breaking into the tens with a full-bodied production-based car was the drag racing equivalent of breaking the sound barrier. It simply wasn't supposed to be possible yet. And then came the modifications. Because if you think a factory Camaro making 616 horsepower was impressive, wait until you hear what happened when the speed shop guys got their hands on it. This is where it gets really interesting. There was a mechanic and engine builder named Connie Kalita operating out of Michigan, and Kalita had a gift for finding the performance hiding inside an engine that the factory engineers had left on the table. He started studying the Camara's intake system and identified something that nobody at Ford had fully exploited. The single 4-barrel carburetor setup, even a large one, created a venturi restriction in the air path. At high RPM, the engine was essentially being choked by its own induction system. The heads could flow more air than the carburetor could deliver. The combustion chambers could handle more fuel than the jets could meter. The engine was being strangled at the point where it should have been singing. Kalita's solution was to strip the carburetor entirely and install a Hilborn mechanical fuel injection system. Direct port injection, one nozzle per cylinder, metering fuel with mechanical precision directly into each intake port. No venturi restriction, no distribution imbalance between cylinders, no mixture compromise between idle quality and wide-open throttle performance. Just precisely metered fuel delivered exactly where the engine needed it, when it needed it. The result added 200 horsepower to an engine that was already the most powerful naturally aspirated V8 in America. Let that number sink in for just a moment. 200 additional horsepower, naturally aspirated. No turbocharger, no supercharger, no nitrous oxide, just better fuel delivery to an engine that was already making power numbers nobody else in America could touch. Kalita's injected Camaro was now producing over 800 horsepower from a cast iron block that Ford had originally designed for truck duty. 800 horsepower in 1965 was a number that belonged in science fiction, not in a speed shop in Michigan. But here's the thing about genuinely talented engine builders. They don't stop when they find something that works. They ask what happens if we push it further. Kalita looked at the Camara's architecture and recognized something that most people had missed entirely. The overhead cam design didn't just make it a better naturally aspirated engine, it made it an almost perfect candidate for forced induction. Here's why that matters. In a conventional pushrod engine running a supercharger, the valve train becomes a critical weak point. Extreme cylinder pressures generated by forced induction put enormous loads on pushrods, rocker arms, and valve springs. Pushrods bend, rockers crack, springs lose their rate under sustained heat and pressure. The valve train, the part of the engine farthest from the crankshaft and hardest to reinforce, becomes the thing that kills your power run at exactly the wrong moment. The Camara's overhead cam design eliminated most of those vulnerabilities. The finger followers operating directly off the cam lobes handled extreme valve spring pressures without the mechanical chain reaction of a pushrod system. The robust bottom end of the 427 FE block, cross-bolted with 4-bolt mains on the center 3 journals, was already overbuilt relative to what the naturally aspirated engine demanded of it. With the heads breathing freely and the bottom end proven strong, Kalitta did what any self-respecting speed freak in 1965 would do. He bolted a GMC 671 supercharger on top of the already injected Camaro and ran it on the dyno. The number that came back was over 1,200 horsepower. Now understand what that means in historical context. In 1965, Formula One engines, the pinnacle of international motorsport engineering, were producing somewhere between 250 and 300 horsepower from engines that cost more to build than most American houses. Top fuel dragsters were running in the 8-second range. Kalitta's blown, injected Camaro was producing 4 times the horsepower of a contemporary Formula One engine from an architecture that had started life as a truck motor. His bounty hunter dragster started running elapsed times in the 7-second bracket when most of the competition was still trying to crack the 8s. The drag racing world looked at what Kalitta was doing and simply couldn't believe it. The technical explanation for why the supercharger works so well on this particular engine goes back to the valve timing advantage the overhead cams provided. In any engine, there's a period called overlap, where both the intake and exhaust valves are open simultaneously during the transition between the exhaust stroke and the intake stroke. In a naturally aspirated engine, overlap is carefully managed, because if you have too much of it, exhaust gases can contaminate the incoming fresh charge. But the overhead cam design allowed Ford's engineers, and later Kalitta's own cam grinding contacts, to run overlap figures that would have been completely unworkable in a pushrod engine. The intake valves could stay open dramatically longer without risking contact with the pistons, because the cam geometry was direct and precise rather than filtered through a chain of secondary components. With a supercharger forcing pressurized air into the intake ports, that extended overlap became a weapon rather than a liability. The pressurized intake charge used the overlap period to help scavenge exhaust gases out of the cylinder more completely than atmospheric pressure alone could manage. More complete scavenging meant a cleaner cylinder. A cleaner cylinder meant a denser charge on the next intake stroke. A denser charge meant more fuel, more combustion, more power. The Camaro and the supercharger weren't just compatible, they were almost perfectly matched at an architectural level, as if the engine had been designed with forced induction in mind from the beginning. The reputation of the Camaro spread through the drag racing community the way rumors spread in a small town: fast, unstoppable, and growing with every retelling. Ed the Irishman Pink, one of the most respected and credentialed engine builders in all of American motorsports, made a statement about the Camaro that got repeated in every speed shop from California to Florida. He called it the most perfectly designed racing engine ever built in America. Coming from a man who had built winning engines for virtually every major manufacturer, that was not a casual compliment. That was a verdict. Mickey Thompson, the land speed record holder and one of the most innovative minds in American performance, started using Camaro engines in his Bonneville cars. The engine's ability to maintain valve train stability at extremely high RPM made it ideal for sustained high-speed runs, where a pushrod engine's valve train would begin to float and lose power just when you needed it most. Jungle Jim Liberman, whose funny car show was one of the most popular attractions on the national drag racing circuit, ran a Camaro. The unlimited hydroplane racing circuit discovered the engine and immediately understood what they had. Miss Budweiser, one of the most famous unlimited hydroplane boats in the sport's history, ran twin Camaro engines, producing a combined output of roughly 2,400 horsepower. The boat dominated its class for years. Here's what most people don't realize about that period between 1964 and 1968. The Camaro wasn't just winning races, it was fundamentally changing how American engine builders thought about the relationship between valve train design and usable power. Before the Camaro, the accepted wisdom in Detroit was that pushrod engines were good enough. European overhead cam designs were for lightweight, small displacement, high revving motors. American performance meant big cubic inches and torque, not RPM. The Camaro proved that was a false choice. You could have the cubic inches and the torque and the high RPM capability if you were willing to put the camshafts where they belonged. Ford officially produced 754 complete SOHC engines between 1964 and 1967. 754 engines. That's it. That's the entire official production run of one of the most significant power plants in American automotive history. Ford sold them through dealerships as over-the-counter racing parts, listed in the performance catalog at $2,450 per complete engine. That's roughly $23,000 in today's money. And here's the thing that makes that number genuinely remarkable. A complete Chrysler 426 Hemi, the engine that had humiliated Ford at Daytona and triggered this entire story, cost about the same amount of money, but it made 200 less horsepower. The Camaro was, dollar for dollar, the greatest performance bargain in American motorsports history, and the people buying them knew it. Now, you might be thinking, okay, so Ford built 754 of these engines and sold them to racers. That's a pretty limited impact, right? Here's where that thinking goes wrong. The influence of the Camaro extended so far beyond its production numbers that it's almost impossible to fully map. Every engineer at Chrysler who got access to a captured example spent hours studying the valve train geometry, the chain drive architecture, the head port design. The lessons they absorbed fed directly into refinement of the second-generation Hemi. General Motors engineers looked at what the Camaro was doing at high RPM and started asking uncomfortable questions about the limitations of their own big block designs. The later Chevrolet ZL1 aluminum big block, one of the rarest and most valuable muscle car engines ever produced, incorporated high RPM breathing lessons that trace a direct line back to Ford's overhead cam experiment. But the really fascinating developments were happening not in corporate engineering departments, but in speed shops and garages across America. Because when you give genuinely creative, mechanically obsessed people access to an engine that's already pushing the boundaries of what's possible, they don't treat it as a finished product. They treat it as a starting point. Harvey Aluminum, a California company specializing in high-performance castings, developed a complete set of aluminum cylinder heads for the Camaro that flowed measurably better than the factory iron units, while cutting roughly 40 pounds from the front of the car. For drag racing, where weight distribution is everything, that 40-pound reduction was worth multiple tenths of a second in elapsed time. Crane Cams, which was already one of the most respected camshaft grinding operations in the country, developed custom profiles specifically for the Camro's overhead cam architecture. Profiles with lift numbers that would have physically destroyed the valve train in any contemporary pushrod engine. 750 thousandths of an inch of valve lift in 1966. That number was so extreme that most engine builders who heard it assumed it was a typo. Moon Equipment, the legendary speed parts manufacturer whose moon disc wheel covers became an icon of early hot rod culture, cast special intake manifolds designed to run multiple carburetors or Hillborn injection on the Camaro. Their dual-quad manifold, running two 4-barrel carburetors on an already free-breathing overhead cam engine, was capable of flowing enough air and fuel to feed an engine making close to 900 horsepower naturally aspirated. Moon sold every one they made within days of announcing availability. Look, what was happening in this period was something genuinely unusual in American automotive culture. The Camaro had created an entire ecosystem, an underground economy of parts, knowledge, and expertise that existed completely outside the mainstream automotive industry. Speed shops that specialized in Camaro builds became destinations. Guys would drive across multiple states to have their engine worked on by someone with a reputation for understanding the Camaro's particular character. Knowledge was currency. If you knew how to properly set the chain tension, how to degree the cams for maximum power at a specific track, how to match the Hillborn injection nozzle sizing to a particular supercharger's output, you were valuable. People paid for that knowledge, sometimes in cash, sometimes in trade, sometimes just in the opportunity to be in the room when the engine fired up for the first time after a fresh build. The chain drive system that everyone had initially worried about turned out to be one of the engine's greatest strengths. Here's what most people don't realize about why that mattered. When Ford's engineers first presented the Camry's timing chain architecture, the immediate objection from almost everyone outside the development team was chain stretch. A 6-foot timing chain running at sustained high RPM was assumed to be a maintenance nightmare, something that would require constant adjustment and replacement to keep the cam timing accurate. Inaccurate cam timing on an overhead cam engine is catastrophic. If your cam timing drifts, your valve timing drifts with it, and your power output drops off a cliff. In the worst case, your valves contact your pistons and you're rebuilding from scratch. But what the skeptics hadn't accounted for was how dramatically Ford had over-engineered the chain system. The chains Ford specified for the Camry were built to a load rating approximately 3 times higher than the maximum tension the engine could theoretically generate at redline. The tensioners were robust, the guides were durable. Racers who were running these engines at 9,000 RPM for extended periods found that chain stretch was almost a non-issue in practice. One engine builder in Florida documented running the same timing chain set for over 200 quarter-mile passes without any measurable change in cam timing. For a part that everyone assumed would be the engine's Achilles heel, that was an extraordinary result. The valve springs were another area where Ford's engineering proved to be ahead of its time. The development team had sourced silicon chrome steel spring wire from an aerospace supplier rather than using the conventional spring steel that every other American manufacturer was running. The material maintained its spring rate at sustained temperatures that would have caused conventional springs to take a set, meaning to permanently compress and lose their installed height and rate. Racers discovered they could run cam profiles with lift and duration figures that demanded enormous spring pressures without experiencing the valve float that killed power at high RPM in pushrod engines. This is where it gets really interesting, because the combination of those overbuilt chains and those aerospace-grade valve springs meant that the Camry's theoretical RPM ceiling was significantly higher than Ford had officially rated it. Keith Black was one of the first engine builders to systematically explore exactly how high that ceiling actually was. Black was already a legend in Southern California drag racing circles, a meticulous, almost obsessive craftsman who approached engine building the way a surgeon approaches a complex procedure. Slow, methodical, absolutely precise. He took a destroked Camry, reducing displacement to 396 cubic inches by fitting a shorter stroke crankshaft, and began mapping the engine's behavior as he pushed it progressively higher up the RPM range. What he found was that with properly matched components, the Camry's valve train remained completely stable at 10,000 RPM. Not 9,000, not 9,500. 10,000 revolutions per minute from an American V8 engine in 1967. To put that in context that actually means something, a contemporary Ferrari 330 GTS, one of the most sophisticated road cars in the world at that moment, redlined at 7,500 RPM. The Camry, an engine derived from a Ford truck block, was spinning 33% faster than a Ferrari. With twin turbochargers feeding those free-breathing overhead cam heads at sustained boost pressure, Black's engine produced over 1,800 horsepower on the dyno. 1,800 horsepower in 1967. The entire United States Navy's destroyer fleet was powered by engines producing less total horsepower per vessel. The number was so extreme that when Black first reported it, other engine builders assumed his dyno was miscalibrated. It wasn't. Here's the thing about what Black and Khalida and the other top-tier Camry builders were doing during this period. They weren't just building faster engines. They were inadvertently conducting advanced research into areas of internal combustion theory that the academic and corporate engineering world wouldn't formally explore for another decade or more. The relationship between valve timing and supercharger efficiency that Khalida had discovered empirically in his Michigan shop was the same relationship that turbocharged Formula One engineers would spend millions of dollars studying in wind tunnels and on sophisticated dynos in the 1980s. The high RPM valve train stability data that Black was generating in California was the kind of information that Japanese manufacturers would use to justify the development of variable valve timing systems in the 1990s. These men were working without computer simulation, without finite element analysis, without any of the digital tools that modern engineers take completely for granted. They were working with micrometers, oscilloscopes, stopwatches, and an almost supernatural intuition built from thousands of hours of hands-on experience. Now, the streetcar story running parallel to all of this competition history is one that doesn't get nearly enough attention. Because despite NASCAR's official position that the Camaro was not suitable for passenger car use, a remarkably determined community of hot rodders had absolutely no intention of keeping the engine confined to the drag strip. The engine's physical dimensions actually worked in its favor here. The overhead cams added height to the engine, which was a consideration, but the overall width of the package was not dramatically different from a conventional FE big block. That meant the Camaro would physically fit into any engine bay that could accept a standard 427, which in the mid-1960s meant a substantial portion of Ford's lineup. The most legendary street Camaro build of the era was almost certainly the Lawman Mustang, constructed by a California shop called Fiberfab that had a reputation for building cars that existed somewhere on the blurry line between street legal and completely unhinged. The Lawman featured a Kalita specification injected Camaro producing 850 horsepower, installed in a Mustang fastback that had been put on an aggressive diet. The finished car weighed 2,800 pounds. The owner, whose identity various accounts over the years have treated with the kind of discretion usually reserved for witness protection participants, claimed the car would accelerate from 0 to 60 miles per hour in 2.8 seconds and run quarter-mile elapsed times in the 9-second bracket on street tires. In 1966, on street tires, California Highway Patrol officers who encountered the car on public roads apparently found the experience sufficiently alarming that the vehicle was eventually impounded on the grounds of being a public safety hazard. Not for any mechanical violation or emissions issue, simply because a car that accelerated at that rate on public roads was deemed incompatible with the continued well-being of other drivers sharing those roads. The Lawman Mustang spent several months in a CHP impound lot before its owner navigated the legal process of reclaiming it and promptly moved it to a private track where it could be exercised without terrifying innocent motorists. Stories like that one circulated through the hot rod community and created a mythology around the Camaro that transcended its actual production numbers. You have to remember that in 1966, the fastest production car you could buy from a dealer was probably a Shelby GT350, which Ford's own Shelby American operation had built from a standard Mustang. That car made 306 horsepower and ran the quarter mile in the mid-14s. The Lawman Mustang was running the quarter mile nearly 5 seconds faster. The gap between what was commercially available and what the Camaro Underground was building was so enormous that it belonged in a different category of vehicle entirely. The boat racing community's relationship with the Camaro deserves its own deep dive, frankly. Unlimited hydroplane racing in the 1960s was one of the most technically extreme motorsports in existence, a discipline where boats weighing several tons were skimming across water at speeds exceeding 200 miles per hour, balanced on a knife edge between spectacular performance and catastrophic accident. The demands placed on engines in that environment were in some ways more severe than anything drag racing or oval track racing required. Sustained high RPM operation, saltwater contamination risk, extreme vibration loads from hull impact with water at speed, wildly variable throttle inputs as drivers managed the boat's tendency to become airborne. The Camaro handled all of it. Miss Budweiser's twin Camaro installation became the benchmark that every other unlimited hydroplane team measured themselves against. The combined output of those two engines, somewhere in the range of 2,400 horsepower depending on the specific state of tune, gave the boat a straight-line speed advantage that its competitors simply could not match with conventional pushrod architectures. The boat won repeatedly, and every time it crossed the finish line first, it was making an argument that NASCAR had tried to silence in 1964. The argument the Camaro kept making every time it won, on the drag strip, on the water, in the back alleys and private tracks where the street builds ran, was the same argument Ford's engineers had made in that Dearborn boardroom in 1964. Overhead cams are the future. The pushrod engine, for all its simplicity and reliability and cost advantages, has a ceiling. and the camera had already blown through that ceiling so completely that you could barely see it in the rearview mirror. The establishment hadn't been ready for that argument in 1964, but by the late 1960s, the evidence was becoming impossible to ignore. By 1970, the camera's moment in the competitive spotlight was beginning to fade, but not for the reasons you might expect. It wasn't that the engine had been surpassed or proven wrong, it was that the world around it was changing in ways that made its particular brand of extreme performance increasingly difficult to sustain. Chrysler's second-generation Hemi had absorbed enough lessons from studying captured camera examples that it had closed the power gap considerably. Chevrolet's big block program had produced a ZL1, an all-aluminum wrap motor that combines enormous displacement with surprisingly sophisticated breathing. The competition had spent 6 years catching up, and they had done it partly by studying everything the camera had taught them. More significantly, the regulatory environment was shifting in ways that would eventually end the era of uncompromising race-bred American performance engines entirely. The Clean Air Act of 1970 set emission standards that made high-compression, large-displacement engines increasingly difficult to sell in street-legal form. Insurance companies had begun the actuarial process of pricing high-performance muscle cars out of their reach of younger buyers, the exact demographic that drove the muscle car market. The cultural moment that had made the Camaro possible, that specific combination of manufacturer rivalry, relaxed regulation, and consumer appetite for raw performance, was closing like a window in autumn. Ford itself moved on. For NASCAR, they developed a 429 Boss engine, a purpose-built racing power plant that worked within the revised rulebook and finally gave Ford a competitive overhead valve engine that Bill France couldn't ban. For the street market, the Mustang was evolving toward a different kind of car. The emission-strangled engines of the mid-1970s were so far removed from the Camry's philosophy that they might as well have been from a different manufacturer entirely. Ford officially discontinued Camaro parts availability through their dealer network in 1967, though the aftermarket had already built enough of a supply chain that the engine continued to be raced and built from parts for years afterward. Here's what most people don't realize about what happened next. The Camaro didn't die. It went underground in the most literal sense, disappearing from official manufacturer catalogs and sanctioned competition results while continuing to exist in private collections, speed shops, and the hands of dedicated enthusiasts who understood exactly what they had. Complete, date-coded, numbers-matching SOHC engines were carefully stored away. Some went into climate-controlled garages. Some went into the back rooms of speed shops where they sat under canvas covers for decades, waiting. The people who owned them understood instinctively that these engines were significant in a way that transcended their competitive results, that they represented a moment of genuine American engineering ambition that wouldn't come around again easily. They were right. Today, a complete, documented, original 427 SOHC engine in good condition commands somewhere between $50,000 and $80,000 at auction, depending on provenance and state of preservation. Engines with documented racing history, particularly those that can be connected to known drivers or significant competitive events, have sold for considerably more. The reproduction parts industry that has grown up around the Camaro is robust enough that you can today build a complete, fully functional SOHC engine from new manufactured components without using a single original Ford part. Companies in Michigan, Ohio, and California produce billet aluminum blocks, CNC machined heads, reproduction timing chain sets, and custom cam profiles that allow modern builders to create Camaro engines that exceed anything that rolled out of Dearborn in 1964. This is where it gets really interesting, because the modern Camaro revival isn't just a nostalgia exercise. It's a genuine performance movement. There's a company operating out of Michigan right now that built what they call contemporary SOHC engines using the original architecture combined with modern materials and manufacturing precision that Ford's 1964 engineers could only have dreamed about. Billet aluminum blocks machined to tolerances measured in 10,000ths of an inch, titanium valves, dry sump oiling systems, electronic fuel injection mapped on a modern engine management computer. Their engines rev reliably to 9,500 RPM and produce 900 horsepower on pump gasoline without forced induction. They cost $85,000. They have a waiting list that stretches nearly 2 years. The customers are not restoring old race cars, they're building new ones. Hot rods and resto-mod Mustangs and purpose-built drag cars that use the Camry's architecture because even 60 years later, it remains one of the most elegant solutions to the problem of making an American V8 breathe freely at high RPM. The deepest legacy of the 427 SOHC isn't in those auction prices or those waiting lists, though. It's in the DNA of every overhead cam Ford engine produced in the last 30 years. The modular engine family that Ford introduced in the early 1990s, the architecture that powered everything from Police Interceptor Crown Victorias to the 540-horsepower Shelby GT500, was Ford's formal acknowledgement of what Al Joniak's team had proven in 90 days in 1964. Overhead cams work. They work better. The Camaro had spent 3 decades being right before Ford's production engineers were finally ready to admit it. Every Mustang GT sitting in a dealership today with its SOHC Coyote V8 singing towards 7,500 RPM carries that lineage. Every F-150 with a twin-turbocharged EcoBoost V6 using overhead cams to extract extraordinary efficiency from modest displacement is a descendant of the engine NASCAR banned before it ever turned a wheel in competition. The establishment tried to kill the Camaro in 1964 and instead created a legend so durable that it's still being built, still being raced, and still being talked about 6 decades later. Think about what that actually means. An engine developed in 90 days by a small team of engineers working under enormous pressure, produced in fewer than 800 examples, banned from its intended competition before it ever competed, went on to fundamentally influence the architecture of American performance engines for the next 60 years and counting. It won championships it was never allowed to enter. It set records in disciplines it was never designed for. It inspired a generation of engine builders who pushed its capabilities so far beyond the original design parameters that Ford's own engineers would have been astonished. And it proved definitively and permanently that sometimes the most important thing an innovation can do is make the establishment uncomfortable enough to try to stop it. Because you can ban an engine from a rulebook. What you cannot do is ban the idea. The idea that American V8 engines could rev freely, breathe deeply, and make power across a broader range than anyone thought possible. That idea escaped the moment the Camry's first prototype fired up on April 1, 1964, and it has never stopped running. What's the most impressive engine you've ever had the privilege of hearing at full song? Drop it in the comments below, because that conversation is one I genuinely want to have. And if this deep dive into one of the most controversial and consequential power plants in American racing history connected with you, make sure you're subscribed, because here at Legacy Motoring, we're just getting started pulling back the curtain on the machines that were too fast, too powerful, and too advanced for the world they were born into. Until next time, keep those engines alive.